Alice, Bob, and Eve explain quantum walk algorithms.
Hopscotch. Haven't been playing this game since elementary school. 1, 2, 3. I keep moving forward one square at a time. It's taking a while to reach the end.
You know, what you're doing reminds me of quantum walk algorithms. They're a fascinating part of quantum computing.
Quantum walks are such a powerful concept. They're the quantum version of classical random walks, but behave remarkably differently.
How is my hopscotch like a quantum algorithm?
Your hopscotch is like a classical random walk, moving step by step along a line. In classical random walks, you might flip a coin to decide whether to go left or right at each step.
Over time, your position follows a normal distribution. You're most likely to be near your starting point, with probability decreasing as you get farther away.
So what makes a quantum walk different?
In a quantum walk, the walker can exist in a superposition of many positions simultaneously. Instead of a coin, it uses a quantum coin that can be in a superposition of heads and tails.
This leads to interference effects. The quantum walker's different paths can interfere with each other, either constructively or destructively.
What does that mean for how quickly the walker moves?
That's where it gets exciting. A quantum walk spreads quadratically faster than a classical random walk. If a classical walker's distribution spreads at a rate proportional to n steps, a quantum walker spreads at a rate proportional to n steps.
It's like if you could somehow explore the entire hopscotch court much faster by taking advantage of quantum effects.
Are quantum walks useful for solving real problems?
Absolutely. They're the basis for many quantum algorithms that outperform their classical counterparts. They've been applied to search problems, element distinctness, and graph problems.
Let me draw a graph in the sand here. For instance, a quantum walk on this graph could find a specific node much faster than classically possible. The Grover search algorithm can be viewed as a quantum walk on a specific graph.
So instead of my one square at a time approach, a quantum walk would explore many paths simultaneously and somehow find the optimal one faster?
Exactly. And beyond just speed, quantum walks sometimes find solutions that classical algorithms might miss entirely due to their different exploration patterns.
The quantum walker doesn't just move faster, it explores the space differently, with probability amplitudes that can interfere and create patterns impossible in classical random walks.
How do scientists actually implement quantum walks?
They can be implemented on various quantum computing platforms, like trapped ions, photonic systems, or superconducting qubits. Each step of the walk involves applying quantum gates that evolve the superposition state.
The beauty is that a simple set of rules applied repeatedly, just like your hopscotch game, can lead to complex and powerful computational processes.
So while I'm hopping one square at a time, a quantum particle would be simultaneously exploring many paths, with some paths enhancing others and some canceling out.
That's it. And that's why quantum walk algorithms can provide exponential speedups for certain problems. They harness the remarkable properties of quantum mechanics to explore computational spaces in ways impossible for classical algorithms.